It is my great pleasure to introduce Dr. Gretchen Fougere. Dr. Gretchen Fougere is an inventor, technology leader, and educator. She has spent her career engaging people of all backgrounds to understand how engineering and design can enhance their lives. She founded STEM Leadership Advisors to partner with non-profit and higher education organizations committing to expanding STEM reach and impact. She was elected vice chair of the board of the Science Club for Girls. Dr. Fougere has had dual careers in education and technology development. In education, she was the inaugural Associate Dean of Outreach and Diversity in the College of Engineering in Boston University. Over the more than 6 years, she launched and spearheaded a nationally impactful initiative called the Technology Innovation Scholars Program, where a cadre of highly trained engineering undergraduates engaged secondary students in hands-on engineering challenges, reaching over 17,600 students. She partnered with funders such as AT&T, NASA, Accenture, Genzyme, and National Science Foundation, and created inquiry-based STEM programs that inspired and challenged diverse students with a variety of learning styles, often in underrepresented and underserved communities. The Massachusetts high-tech community recognized Dr. Fougere as a mass tech woman to watch, and Carnegie Corporation 100K in 10 appointed her a fellow. She advised the Society of Women Engineers and Graduate Women in Engineering and Science. She actively collaborated with engineering and education faculty at Boston University and beyond, and secured over $25 million in funding. Additionally, she was a senior leader at the Possible Project and at the groundbreaking Engineering is Elementary program at the Museum of Science, where she worked on partnerships, curricula, and professional development. Dr. Fougere also has a decade of technical and managerial experience in technology development. Her industrial experience includes leading a 20+% advanced research and development organization at Duracell and developing technical products and new business in high-tech and aerospace sectors. She received her PhD in material science and engineering in the field of nanotechnology from Northwestern University and was elected to Sigma Xi. Her research was conducted in Argonne and Oak Ridge National Laboratories. She received bachelor's degree in biomedical engineering and mechanical engineering from Vanderbilt University. She holds 3 U.S. patents. And I'm honored to say that this event was funded by the request of Dr. Mike McShane. Unfortunately, Dr. Mike McShane couldn't be here today, but he has done a wonderful and generous job in making this event happen. Dr. Mike McShane is the department head of biomedical engineering at Texas A&M University. Dr. McShane is committed to supporting women in engineering and particularly encouraging women in biomedical engineering to develop the skills to take on leadership roles in their respective communities. As such, biomedical engineering at Texas A&M University is heavily promoting pursuit of advanced degrees to its undergraduate and prioritizing recruitment and retention of female graduate students, postdocs, faculty, and providing opportunity to build leadership skills. this event is one example of this commitment, which can also be seen in the sponsoring of other diversity programs in IEEE society. Texas A&M University is one of the largest full-service universities in the world. It is a top-tier research institution with expenditure approaching $1 billion annually, and the commitment to technology transfer and support economic growth. The university has a progressive faculty and an ethnically diverse student body that is about 50% women. Women also represent key positions in the university's leadership, including the deans of engineering and medicine, both National Academy members and the provost. The Department of Biomedical Engineering is sponsoring this event because it aligns so well with both its technical and outreach goals. The department is known for its translational research with bioinstrumentation represented in roughly half of the research portfolio. The department also currently has women at all faculty rank and is further committed to providing opportunities for faculty as well as students and postdocs. Therefore, the Department of Biomedical Engineering is honored to partner with IEEE EMBC to sponsor this event and to promote diversity and inclusion in biomedical engineering community. Please join me to thank the sponsor and welcome Dr. Gretchen Fougere.
Thank you, and good afternoon. I'm really excited to be here to talk to you about something that I really care about and something that I think is important for all of us. And when we think about moving women and the percentage of women in engineering for something that's considered an oxymoron right now to something, a redundancy, I'd like to just share a little bit about my story and my journey and hopefully spark some interesting dialogue with you at the end. And I have a challenge for you. For those of you in the room, I'd like to hear from at least 10 of you with questions for me. And if you do, I'll provide some bonus insight at the end of this presentation. Deal? Okay, thank you. All right, so this is what we're going to do today. We're going to talk about why engineering and women in engineering is important, and then why I care about this and the things that I've done throughout my journey. We're going to talk about the system, and unfortunately the system I know about is the United States system in terms of how do we create engineers. So there's an opportunity for us to learn from one another because this is an international conference. I'm going to tell you some stories about my work in the technology world as well as in education and how we can capitalize on that and learn from that. And hopefully you'll relate to some of the stories both as somebody who's a researcher and a former student or a faculty member. We're going to talk about how women move through the system and become engineers and where they may encounter barriers or where they may actually choose to do something different. And this provides insight and opportunities for us to work in that system and some levers that we might be able to act upon. And it's really good to talk about things, but it's much better to act. And I'd like to share a list that I created that hopefully you can learn from and use to actually put in action if this is important to you. And I hope everybody in the room is open for a little discussion, a little learning, and a little journey together right now. And thank you to the sponsors, and thank you to Professor McShane for sponsoring this talk. So, how many of you traveled here by plane? Quite a few, right? For it's an international conference. Well, when commercial airplane travel started in the 1950s, those planes were designed by men and tested by men. So that's the bottom line. What happened was the commercial airplane industry was just starting and it needed to be very professional. So there was a strict guidelines on what women air hostesses could wear. So you can see this woman is very formally dressed and she has sharp high heels. So in the course of traveling up and down the plane during its flights, those sharp high heels started puncturing the floor. And as they did, the floor failed. So this is an example of why women not involved in the technology innovation process can have negative impacts on the design. Trains. How many of you took the S-Bahn or the U-Bahn or maybe another Bahn or a high-speed train to get here? Great. All right, so in World War I, there was a labor shortage, and so women were brought into the train industry They were operating trains and cleaning trains and actually doing some of the physical work if they had the capability. They were also doing some of the machining, which I think is very interesting. And after the war ended, those women lost those jobs. So we had a loss of trained talent. All right, how many of you drove? If you were lucky, you got to drive fast on the Autobahn. What's it called, the fast, where there's no speed limit? I don't remember. Anyway, airbags. We all consider airbags as something that protects us all, right? And 20 years ago, when they were first developed, they were designed for men only. And as a result, they were actually damaging women, and women being hospitalized because the airbags themselves were causing injury. So for about 20 years, it took time for those to become mandatory, that you would test women types of crash test dummies with a very, very different body type. So here's an example where women were not involved in the designing or the testing process, and it was actually caused a safety issue. So planes, trains, and automobiles. It's a funny movie, right? But what does that have to do with women in engineering? It's a lack of women in engineering that created a deficit in terms of the technologies that were developed, and also limited the trained talent and what we were able to tap into in terms of brain power and creativity in developing technology and moving us forward. So if we can provide opportunities for women to enter engineering and stay in engineering, it's going to have a benefit to society, it's going to have a benefit to the technology we develop, and the research that we progress. So why do I care about this? This is a picture from my high school, Honor Society. In the United States, this is a group of students who have done very well academically, and they have some leadership skills. And one of the first things you'll notice, this is in Memphis, Tennessee, is that this group is about 50% women. It's also about 50% African American students. All of these students were doing just as well as I was, but didn't have the opportunities, the encouragement, the inspiration, and the preparation to study engineering. So just think about if we had all of these people involved in engineering, what a benefit that would be to all of us. Anybody figure out where I am? All the way on the left, the only geeky one in the jacket, right? Great. All right, so in the United States, we talk about where engineers come from, and we're all engineers. We like to talk about systems. We have inputs and we have outputs, and we have decision points along the way, because these are people, and these are people who are making choices. In the United States, in primary school, everybody's curious. They want to learn. When they get to secondary school, they start to make decisions, and those decisions can affect what kind of math and science they take and what they're capable and prepared to do in college. When we think about students who come into our programs, they have a choice to make. They need to have taken the right math and science, they need to be ready, and they need to see themselves as engineers. And they have other choices to study as well. Now, how many of you in the room are graduate students? Okay, how many are faculty? Postdocs? Great. So you made a choice at some point in time to go to graduate school or to go into industry. But what if we made that choice more apparent to people? Wouldn't it be great to have more of that talent working with us? So if we think about where we are and the roles that we might play in this system, you're all educators and you're faculty, you're researchers, you're people who love engineering, love thinking about it and solving problems. And you can work with folks as a mentor or an ally. We talked about, President Shankar joined us last night and talked about not having the right chromosome to be a woman in engineering. But you can care for that and you can work on that and you could be an ally for that, regardless of who you are. And those of us in technology development, if we had women in engineering, that would be helpful as well. All right, so how did I first decide that I wanted to be an engineer? Believe it or not, it was because of a TV show. And this really inspired me to become a biomedical engineer. How many in the room are studying biomechanics, biorobotics, neuroprosthetics, right? Raise your hand. All right, well, you'll get a kick out of the leg here, right? You can see all the circuitry and the mechanical stuff that she has going on. But this was a woman who was a teacher, and then she was like a superhero. But what I loved about her was she was helping people, and she was also using technology to do that. And that's what really inspired me to study biomedical engineering. I went to Vanderbilt. I got my bachelor's degree in biomedical engineering, and partway through, I figured out that there weren't a lot of jobs for people in biomedical engineering at that time. Most of my friends were going to graduate school or they were going to medical school. I needed to get a full-time job. I needed to be able to help my family. And so I double majored in mechanical engineering. So I'm going to talk to you a little bit about the successes and challenges that I've had along the way. And this is novel ground for me, so I hope you feel comfortable with it, and I hope I feel comfortable with it. It was expensive. It took me another semester, so all my scholarships, all my financial aid went away, but it worked, and I really loved mechanical engineering. My grades went through the roof. Because of my training in the urban underserved school in Memphis, Tennessee, was not prepared for college. I'd taken all the right math and science classes, but I still didn't have the study skills. So it's something we want to think about as we start to encourage more women to stick in engineering. My first job was as a mechanical engineer. I was a designer at Pratt & Whitney Aircraft, and this was really cool. For somebody that was interested in materials, this was like a dream come true. This is the PW4000 engine. It powered wide-body airplanes like the 747 and ultimately the 777 Dreamliner. I was one of very few women. So picture a room this size, about 200 desks, right? And the big shots had the bigger desks, and maybe they had a little cubicle or a wall or something. About 200 people were all working on this jet engine, designing it, and being the technical folks for this. And there were probably about 10 women in the group. And then there were administrative assistants sprinkled throughout. So it was very important for me to look different from those women and to dress up and to make sure that they understood that I'm an engineer and not just somebody that schedules the rooms. I was invited to join a rotational program, so I got to work on different parts of the engine, designing different parts of the engine, which was really cool. And one of the things that really stuck with me, and those of you who are in the room are very driven by data and making decisions based on data and analytics and things like that. Machine learning is all over this conference, which I love and I'm really excited about, is quality improvement. And if you've heard of Deming, you've heard of Duran, you've heard of total quality manufacturing, those types of things, we learned about the process of developing this engine and how we can make small tweaks and understand how we can improve the efficiencies and reduce cost. So that kind of embedded in me a mindset that we always want to continuously improve what we're doing. One of the challenges that I had was the fact that you go from this room where you're designing something on your board, a big picture of what you're working on, and I was working on the high pressure turbine here. This, for reference, the fan, the front of the engine is about 100 inches, so about 8 or 9 feet in diameter. I was working on these major rotating parts right behind the burner. So these are temperatures that are close to the melting point of these materials. These turbines are spinning at 10,000 RPM, so you can imagine there are huge thermal loads and mechanical stresses on these materials. And I was designing them to last for a certain period of time and to make sure we extracted as much energy and provided as much thrust and lower fuel costs for the engine. So this is really cool, and you could tell I geek out on this stuff. But anyway, one thing that was interesting was we'd be on our boards, we'd be drawing these great pictures, and then we need to go down to the shop if they asked us questions. So when you're walking through this shop, you can imagine there are no women. It's all operators on equipment very similar to this. And as soon as they hear your shoes, they look up and stare at you. They stop what they're doing. But I went down to talk to this guy who was machining my part that I had designed, this turbine. And I'm talking to him, and he's asking me a question about a surface finish or something. And I'm standing there on this wooden platform that he had, and all of a sudden my high heel went through the platform. So now I'm standing like this. And I'm trying to decide, do I make a big deal about this, because already I'm kind of an oddity out here, or do I acknowledge the fact that this is kind of funny and we can have a joke about it? So I took the joke route. I said, excuse me. So I pulled my shoe out, and then the other one was down. But anyway, he and I resolved this technical problem with the turbine. We became friendly, and it became like an icebreaker. And I'd like to just acknowledge that humor goes a long way for helping us with things that are really tricky, which is diversity. I quit my full-time job to go back to graduate school, and I really was excited about the opportunity to work in materials science. I was accepted to MIT and Northwestern and a couple other schools and chose to study at Northwestern. And when I was there, I initially was going to do a master's degree, but Professor Wertman, who was the chair of our department, quote unquote, seduced me into coming into her lab and doing a PhD. And it was really exciting because nanotechnology in the 1990s was very, very early. Those early days, we didn't know about fundamental properties, and we were studying mechanical behavior, which was something I was really excited about. I had some challenges along the way, some of which involved just actually handling these materials and actually testing these materials. So my advisor said, I don't know what to do, and so I ended up writing a proposal to go do research at Oak Ridge National Lab to actually do some testing and some characterization. So I wasn't going to give up because I thought there was another way to do this. One of the things I did that was interesting was based on my design experience, is built a high compaction unit inside an ultra-high vacuum. So this is an ultra-high vacuum with 25-ton press, and we're taking the nanocrystalline powder that we've made that's very pristine and making it into something solid where we can do some cool testing with it. That became a core processing unit of the lab, and there were a lot of folks in the machine shop there and other researchers who helped with that process. One of the things I also did in grad school was actually started my outreach activities. I worked with younger kids so that they knew about math and science to be on track to go to college. So again, we talk about preparation. And how many of you are here, you're sponsored by your research group, your faculty has a grant for you to travel? Great. That is a wonderful opportunity, not only for you as an individual to talk about your research, to present your research, to do a poster, whatever it may be, but also to network with folks and get some face-to-face interaction and talk about things that you love. And I would recommend that that's something that we all think about doing. I had the privilege to go to 4 international conferences and talk about my research, which is a great opportunity. So I went back into the real world and worked in energy storage at Motorola and completed my dissertation while I was working full-time. I would not recommend that. Motorola wanted me to start early, so I kind of did that and did both for a very long time. So we were developing energy storage devices for our handheld devices as well as for satellite phones, and thinking about different novel combinations of materials that we could put together to create very high rate capability devices. So I want you to notice 2 things. This is my desk, right? You can see how old I am by the thick computer here. But you can also see that in both cases I'm wearing my safety goggles. We need to be frugal as engineers. No, I'm just kidding. But anyway, these are my safety glasses. I actually had a child when I was at Motorola, and it was my first child. And of course, this was after I did dissertation. But I got promoted after I came back, and it was the first time my manager had ever had a pregnant employee. So it was a novel thing for both of us. We patented a lot of our work because we were trying to create a business for Motorola out of these energy storage devices. So it was a really exciting time to be at the fundamental piece of R&D. And then I went to work for Duracell, also in energy storage, and now I was working, had a large development team that was working with me, electrochemists and engineers and technicians. And that was actually in Massachusetts, so that's how I ended up in Massachusetts. Because I had done the outreach in graduate school, I had an opportunity when Duracell decided to relocate. I did not want to relocate with them. So I was privileged to be able to go into education. And I taught in the classroom, I taught in after-school programs, and really focused on helping students understand math and science and how engineers solve problems and really have fun, right, and do some hands-on stuff. I ended up working at the Museum of Science in a program called Engineering is Elementary. It is a curricular program that elementary teachers teach in the classroom, and it all starts with a storybook that introduces a problem that a child across the world has. And I'd like to just share one because it's kind of interesting for those of us in the audience who are biomedical engineers. This is Eric, and Eric is hiking in Germany with his sister, Gretchen. I got to be part of the team. That was nice. And he stumbles and falls, and he has to figure out how to get down the mountain. So all of his sister and his friends, they put together a splint. So kids are putting together a splint in this lesson and thinking about how to solve a problem, what their constraints are in terms of materials and time, what the criteria for success is. So you can see there's some math and some things built into this process. And what was great about this experience at the Museum of Science is the curriculum was very, very relevant. I had taught it in my classroom, and it was authentic in terms of introducing the different fields of engineering. I wanted to go to a bigger platform. I wanted to work with engineering students, and I had the opportunity to join Boston University. Dean Luchin, who was president of EMBC, created my role as assistant dean in the college, and I inherited one engineering educational program and then started 3 others with partners across BU and beyond. And as we heard in the introduction, we grew those programs such that we were reaching kids nationwide. So we're actually thinking about building the pipeline, not just for our program at BU, but also for other programs, and helping kids get excited about engineering early on. We primarily worked with underserved schools, so schools that did not have access to engineering and didn't necessarily have any enrichment. And the programs that we started and run grew from very small with a little bit of seed money to bigger and proven and measured type of programs. And we did that with a lot of great partners, as we heard earlier, including the current Family Foundation, which gave us the seed money. So industry was really important in this. They wanted to work with me because we were helping school kids as well as helping engineers. So they had, workforce development incentive there. So one of the programs I'd like to spend a little bit of time talking to you about is called the Technology Innovation Scholars Program. And this was started with seed money from the Kern Family Foundation. And what we did was we recruited undergraduate engineers to help us serve as teachers in classrooms and guide kids in engineering design challenges. So these are a couple different cohorts of students. Initially I had 15 engineers and I grew it to 60. And I trained them in how to do inquiry-based lessons, how to talk to people about engineering in ways that made good sense. And we learned a lot about the technology and the research that was being done at BU because we were taking that and translating it into something that kids in middle school and high school could understand and engage and build something related to it. So they might learn about clean energy and they would get to build their own wind turbine. And they would understand how the wind turbine worked. It would fail and they would laugh about it. They would determine how much it costs. So all the types of things that we think about as technology innovators, we were helping kids and younger students in schools across the country do. We primarily targeted underserved schools because they don't have access to doing hands-on work. A lot of them don't have access to even doing basic science experiments, much less engineering. And their teachers don't necessarily have the skills or the training to do this. So this was a really nice opportunity. One of the things you can tell by these pictures is that we had a lot of diversity built into this program, and this was a happy accident. The engineering undergraduate students that applied to work with me were about 50% women and about 27% underrepresented minorities. And in the United States, those are Latino students and African American students. And I thought this was wonderful because this happy accident meant that these engineering students were going to be looking like the middle school and the high school students that they were working with. So they were near peer models that actually had an added benefit of diversity built in. We also developed quite a community. I'm close to a lot of these students still. I've helped them with jobs in graduate school, and they became friendly with one another. And when you are an only, you're sometimes lonely, so it's good to have friends that you can do things with. These students actually learn more about engineering and technology by being able to teach it too, which I thought was neat. And in the course of teaching engineering and getting kids excited about doing engineering, it reinforced their engineering identity. And we'll look at some research in a minute that shows how important that is. The other thing that was interesting was the corporations that we contacted through my partners at BU, like AT&T and Accenture and others. They were really interested in hiring these engineering students because they had leadership skills, presentation skills, and they were going to hit the ground running when they started their full-time jobs. So, engineering and medicine and biology. I thought this would be a good example just to give you some insight into what we were doing in the schools. So this is the design process by which schools in the United States are asked to teach. And it has to do with how engineers develop a prototype and solve a problem. So in this case, the problem that these students were solving was cancer. And they were able to choose what kind of organ they wanted to treat. And then they had to figure out a way to process the chemo treatment. And obviously, we're not really doing those things. These are all models. So if you look at this platform here, this ramp here, This is a model of different organs, and there are holes here which are supposed to represent pores of different organs, like skin or breast or lung. And this student here is actually creating the nanotechnology beads that represents the chemo. So they do a lot of processing, they do a lot of experimentation to make those beads, they do some math and some analysis to figure out how predictable that process is and to get some statistics. And then they match it with the size of the pore in this organ to see how well they've targeted it. So I think it's really important that it's something that kids care about. Unfortunately, everybody knows about cancer and they've had somebody in their lives touched by that. And it's a way for students to understand that engineers solve problems that help people. They solve problems that make our lives better. And they're working on things they're going to help all of us. And they can be part of that process. So here's an example of one of our, 15 lessons that we put together when I was at BU. So let's talk about why women are going into engineering and what's the data behind the trends that we are seeing. So again, I'm going to just emphasize the fact that I'm only familiar with the United States system of engineering and education, so I'm just going to remind you of that. But I'd love to learn about more. So in primary school, what happens when kids get into middle school, they often have to choose or they're placed into what advanced math and science they can take. What we've seen is that boys and girls are performing just as well on standardized tests, national tests, in terms of their math performance. So it's really able to do this at that time and make them motivated to take more math and science. And even if they don't end up becoming engineers and they go into other programs, we all know how important it is to be competent in math just to get into college, right? Engineering identity and seeing themselves as engineers, we need to think about what is it that we portray. I like the bionic woman, right? But that was me. But are we portraying ourselves as perfect, geniuses, somebody that never makes a mistake? We all have. We don't make mistakes, but we all make mistakes, right? And we learn from that and we persist. Otherwise, we wouldn't be doing this hard work that we love. When these students get to college, more women than men are actually going to college in the United States. So we really have an opportunity to capitalize on that talent. But again, you have to be prepared and you have to have had the readiness before you get into college. What we've seen in terms of the disciplines in the United States is biomedical engineering is actually doing quite well, right? It's close to 30 or 40% women. Computer engineering, electrical engineering, not so much. And I really challenge all of you to talk about the machine learning in a way that really excites young people, because that's an opportunity to show how electrical engineering and computer engineering actually feeds into something related to healthcare. It's a real opportunity to capitalize on. What happens too in young women, they're more likely to take themselves out of engineering in the first 2 years because they don't recognize that this is a hard curriculum, right? And they think that it's only hard for them and not hard for everybody. So and some of the studies have shown that they're doing just as well academically as their male counterparts. They just don't recognize it. So we can have frank conversations with them about the challenges that we've had, and we can encourage them to persist through that. And really focus on the first 2 years of college. Kids change their mind about what majors they want to pursue, right? But we want to make sure that those who are really interested in engineering can stick with it. All right, so what's the research? How are these students seeing themselves as engineers and ultimately becoming engineers? So I like to kind of paraphrase things because it makes it easy for me to understand. When we worked with young people, we always made sure that what they were doing from an engineering standpoint was fun, right? And the first thing somebody asks when they're being taught something is, where am I ever going to use this? Well, what does this have to do with me? Well, why do I need to learn this, right? But if you talk to them about something they care about and you engage them, then you're going to engender some engagement and some affinity for that subject matter. They also need to feel successful. It was important for us to have students that were doing these design challenges to fail and to improve. And the reason they knew that they'd gotten better was because of math, right? So here's an objective measure of how good you are at something. They need to be able to see themselves doing this. This is a long haul when you talk about somebody in middle school who's maybe 12 and taking algebra, completing an engineering degree when they're 21, right? That's a long haul. And they need to be able to see themselves doing this and see themselves as being successful. So self-identity needs to become engineering identity as they go through that process. All right, so now the penultimate list of 10 actions. And what I'd like to do is like go through each one of these, because I think there's an opportunity for us to dig a little bit deeper in this and still leave plenty of time for you to ask me questions. All right, so marketing. Marketing is really important. I think you guys have it in the bag. I mean, engineering for medicine and biology, that has people, that has healthcare, that has quality of life all over it. So you have a huge opportunity not only to influence biomedical engineering, but other fields that you work with. Partnerships. I worked with First Robotics. I worked with 100K and 10. I worked with many, many teachers in the public schools. You need to figure out what they need from you and make it work for them. You know, not impose things, but actually find a way to complement what they're doing, because if kids aren't inspired and they're not ready for engineering, they're not going to be in your programs. Be a role model. We can all be a role model. It's a question of understanding who we're speaking to and making it relevant for them and encouraging them. And we can also be allies if they happen to be somebody that's a little bit different than us. I think it's really important to acknowledge that we all fail and we all learn from that, and there's nothing wrong with that. I think that's why it's really important to try something and learn what worked and what didn't work and try again. And we do that every day in our labs. We do that every day when we teach a class. It's something that we can acknowledge, so we can get rid of the stigma that you have to be a genius, you have to be perfect to be an engineer. Professional development. We talked about the fact that many of you here were sponsored to come to this conference. I think that's a really great opportunity to get out there, talk about your program, talk about your research, get in the community, take advantage of ways that you can get with people that aren't experts, but you can get them excited about what you're doing. Affinity groups. How many of you guys are in the Society of Women Engineers? It's an international group for women. And these types of groups are really great, and you don't have to, it's not rocket science. It's a question of understanding who they are and what they might want and encouraging them to take advantage of national conferences and speaking engagements and be part of something bigger than they are. This is something that might cause us a little pause. And what I mean by this is, think about the faculty in the room. Think about a faculty search and how many women you may have on that search, or any kind of committee. And when you have a very few people, it's that type of person talking as opposed to someone talking. So say you have 10 people on a committee, 3 are women, and Jane says something. Jane is saying something. It's not a woman saying something. So be careful and try to drive towards greater representation, but also be careful that you don't treat people that are a little bit different as tokens and you don't exploit them, for lack of a better word. Make sure it works for people. And also, please don't assume that just because somebody's a certain gender or demographic, that they're actually a champion for that. Maybe they just want to keep their nose to the grindstone and do their own thing. So just be cautious about how we treat one another. A tipping point. When we get to 30%, then it becomes less about what kind of person that is and more about what that person is providing. And that's a really good measurement and goal to drive towards. And as students, if you're going to work with middle school students and high school students, and undergraduates, especially in those first 2 years, keep connecting what they're doing to the career. What's their long-term goal? And make sure they understand that, yeah, you got to take chemistry now, but you're going to have the foundation to be able to be someone who's driving change in synthetic biology or whatever it may be. So just keep connecting them back to what they want to do and reinforcing their desires. And last but not least, this is hard. It's people. It's hairy. It's sometimes uncomfortable, right? But let's take a deep breath. Let's have a sense of humor, and let's be curious about one another, because I think if we can all do something together, we can make a really big change, and a really big change that's important to all of us. Thank you very much.
Thank you very